Assalamualaikum and very good day. My name is Muhamad Syfiq bin Soekarno. I am sales and service engineer of instrumentation in oil and gas application at Teras IoT Sendirian Berhad. So today we're gonna review our paper for solar power irrigation and monitoring system for okra cultivation. First and foremost, our paper of solar power irrigation and monitoring system for okra cultivation focus on three important elements. The three elements that we focus are water, solar energy, and IoT. As we know, water is required for a lot of things such as drinking, irrigation systems, constructions, and power generation. So, there is a necessity to transport water from its source to where it is needed. Water scarcity is a major challenge in agriculture, especially for crops like okra. Traditional irrigation methods often rely on fossil fuels and are inefficient. The second element is solar energy. Solar pumps can improve water accessibility. Groundwater is the only available water source in countries with economic water scarcity or when surface water must be transported over long distance. By harnessing solar energy, we can provide reliable water supply for irrigation even in remote areas. The third element is IoT. In this paper, we propose a system that uses IoT technology to monitor soil moisture and optimize irrigation scheduling. This is for ensuring efficient water usage and maximizing crop yield. Let's talk about the development of solar power irrigation and monitoring system. As you can see in this slide, the whole system consists of three main blocks. As you can see, the development of this whole system will be integrated into the NodeMCU ESP8266. As we know, NodeMCU ESP8266 needed a constant supply for them to be working. To tackle these problems, we propose solar powered system. So, the monocrystalline solar panel will convert sunlight into electrical energy using solar charger controller, and then the electrical energy will be stored into a lead acid battery. The second block in this whole solar power irrigation and monitoring system is the irrigation system itself. So, this block consists capacitive soil moisture sensor, temperature sensor, humidity sensor, and pneumatic diaphragm, which is the water pump itself. So, like I said earlier, we use IoT technology in this system. So, we use a Blynk application for the monitoring system. So, all the data that collected by the sensors will be into the NodeMCU ESP8266. In the same time, it will link with the Blynk application for us to monitor the system. Let us talk about the whole process of solar powered irrigation and monitoring system. As we can see in the flowchart, the NodeMCU ESP8266 will power up by lead acid battery. So the function of the solar panel is to detect sunlight and charging the battery. As I've told in the previous slides, the NodeMCU ESP8266 will be the brain for this whole system. After the microcontroller is powered up, it goes a lot of process based on the programming code that we have set up earlier. First, the microcontroller will start up their Wi-Fi connection and authorization. In the same time, it will also collect the data from all the sensors. So, the soil moisture sensor will detect and give the data to the microcontroller as we said. So, in the flowchart, we can see that we set the sensor reading if less than 30% of moisture in the soil, the water pump will on. So, all this process will be collected by the NodeMCU ESP8266 and will be displayed into the Blynk app. So, this process will be in continuously loop. As you can see the pictures in the slide, this is how we set up the whole solar powered irrigation and monitoring system. So the first one is the schematic diagram of the whole system, and the second picture shows how in the real life that we set up. The sensors and outputs were connected to the NodeMCU ESP8266. So the solar charger controller was fitted to regulate the flow of the electricity produced by the solar panel. Next, we'll be talking about the development of solar-powered monitoring system. As I said earlier, the soil moisture sensor, the humidity and temperature sensor, and also the status of water pump can be monitored using handphones through Blynk apps. The whole process was done using the NodeMCU ESP8266 as their brain. Also in this slide, we show a part of the coding program that we've put into their brain. Next, we're gonna move on to the results and discussion in this paper. In this paper, we presented a few set of data and readings for a different type of sensing. The most important data that we recorded is the soil moisture reading. This reading, as shown in the slides in the middle top, are recorded for over 4 days. The soil moisture of the okra plant was measured using a soil moisture sensor, which consistently reported readings above 70% throughout the 4 days. The readings by the sensor are a lot of difference throughout the day. So this is determined that the capacitive sensor could detect moisture inside the soil. That is also indicates that the plant receives water continuously throughout the day as the soil absorbs water from the water tank. Moving on to the next measurement, that is temperature and humidity. But in this slide, I've only shown you the temperature readings. So actually the temperature and humidity readings are recorded over 4 days, same as also the soil moisture reading, but this time it was taken at a specific periods between 8 a.m. until 5 p.m. So the reading is taken using DHT11 sensor. The sensor detects temperature and humidity in the air surrounding the plants and send the data to the NodeMCU ESP8266. So the results indicate that the humidity reading was inversely proportional to the temperature reading. As the humidity decreased, as the temperature rose, and vice versa. Next, voltage and current readings produced by the solar panels were also recorded and were put together in the paper. So the solar radiation acquired from the solar panel result in a progressive increase in the voltage readings during the morning and throughout the day. However, there is one day that the readings are subsequently dropped sharply. Is because it's raining that day. Next, in our discussions and results, the observation on the growth of the okra plant were tabulated in the paper. So as we can see, the seeds were planted in a pot on week 1. Throughout week 2 until week 4, the okra plant started to grow flowers and the okra fruit started to grow. So the conclusions and the findings of this study show that it is possible to maintain the required level of soil moisture for the okra plantation using solar power irrigation and IoT based real-time monitoring system. So the whole system will successfully maintain soil moisture content above 30%, which is the most ideal for okra growth and ensure renewable energy supply for powering the irrigation system. So all these findings support the possibility of utilizing solar powered system as an efficient and renewable source of supply. Thank you.